All right, welcome back, sterile processing professionals, facilities folks, operating room, materials management, supply chain, surgeons, surgical techs, nurses, you name it. We are so excited for all of you who are tuned in with us today for this really exciting second annual water quality conference titled Uncharted Waters, Equipping Sterile Processing with a Roadmap to Compliance. Now, I don't know about you, but since last year, water has been a really hot topic, a topic that's been top of mind for a lot of sterile processing departments, and rightfully so. Water is such an important part of what we do to prepare instruments safely. I am so excited for this presentation. I have with me today Len Sparks. Len is the Director of Operations at Verda Water Quality Systems. He's a seasoned technical leader and has led many project improvement teams, including providing compliant water purification systems for SPD departments around the world. Most recently, in 2018, he led a project that resulted in developing the most TAR 34 compliant water purification system in North America, which is something really, really cool that I know he's proud of, and I know he's excited for folks to learn more about. In this presentation today, he's going to talk about a case study when something goes wrong with water. As we all know, water is fundamental to the processing of medical devices, but there are so many problems with water quality that can cause really serious issues in sterile processing departments. And during this session, Len's going to explore 4 real-world case studies that reveal what can go wrong and how to prevent or plan for the inevitable. So without further ado, and I encourage everyone, please submit your questions for Len in that Q&A tool on the bottom left-hand side of your page. But without further ado, I know you're not here to see me, you're here to hear from Len. So I'll turn over the virtual stage to Len. Welcome.
Thank you. Thank you. That was a wonderful introduction. I really appreciate that. So yes, just to reiterate, I'm going to go through some real life examples of how poor water quality has impacted our customers. A little bit more background myself. I've been at MMIC for over 10 years, leading the development of AMI TR 34 compliant water treatment and monitoring systems. We develop systems that go into hospitals, into mobile trailers, into temporary facilities, and yes, even into an airplane. And over those years, I've come across numerous customers with horror stories, and they're at their wits' end, and they're in desperate need of a solution for their water quality issues. So I'd like to share a few of those stories with you and give you some insight into what others in your shoes have had to deal with and how they solve their problems. So first, some background. There are many ways water is used in the SPS. It's used in soaking, washing, rinsing at sinks and washer disinfectors. It's the agitating fluid in the ultrasonic cleaners. Water is used in several processes and sterilizers. It helps generate the steam. It generates vacuum in some cases. It can cool vacuum pumps. And the water can be used for blowdowns if the sterilizers have integrated steam generators. So issues with water can cause insufficient decontamination or sterilization of instruments. When we talk about water quality, we're also talking about adequate water pressure and temperature. So low water pressure, like momentary dips in water pressure or spikes in water pressure, can cause equipment faults. Likewise, if the water is too hot or too cold, these can cause faults. Faults means restarting or repeating the cleaning process, resulting in the SPS throughput hits. This can cause surgery delays and cancellations. If the reprocessing equipment has mixing valves, the ability to adjust blended water temperature is within the SPS or is within the facility's maintenance department to control this. If there is hardness in the water, that may be something that the facility is controlling with water softening. The facility's hot water, for instance, may be softened, while its cold water may be not. The facility's water pH may not be something that the facility can control or adjust. It may vary depending on treatments that the local water department is doing to maintain the quality of the municipal water supply. Or they may increase the pH to prevent lead from leaching out of aging pipes. when the pH raises above 8.5, if you have an RO system, those membranes are compromised and the product water quality suffers. And any water that's over a 9 on the pH scale, AMI deems to be inadequate for sterile processing. Now, we deal with customers whose water exceeds 10 on the pH scale. So some parameters may vary over the course of the year as seasonal changes impact the water supply, like runoff into the water supply with the springtime thaw, or municipal water authority changes the actual source of the water in the course of the year. Like in the summertime, they pull from a different source than they do in the winter. Knowing the details on changes to the municipal water supply, it's not your responsibility, but understanding that relationship between the water that you use in the SPS and how it impacts the instruments being processed should be. In every SPS should have a water quality assurance plan. 1, what is the validation and verification plan that you have for a new system? 2, what parameters are going to be monitored? 3, where are they going to be monitored? Where are the sampling ports? 4, what ranges or levels which are going to be there to trigger an action? 5, what's the protocol when there is an actionable event that happens? And 6, is there a mechanism for documenting the root causes of the issue and how will this be prevented in the future? Right, so all this should go into your plan. So how does water impact the work in the SPS? So as water moves through this process, it can become affected chemically and mechanically. And every time it touches something, there is an exchange that can cause problems. So water comes from an immiscible source. This source can change seasonally, which affects the quality of water. It can also change with temperature, with seasons, and sources. The municipality that will treat the water before it arrives at your hospital to make it potable. And from time to time, they need to change how they treat the water to address a specific problem. And this could affect processes that touches the water. A dramatic example of this was in Flint, Michigan. So in order to save money, the city decided to change from Detroit's water supply, which came out of Lake Huron, to a local river, Flint River. The new water began corroding the existing municipal piping and leaching lead out of pipes. Residents complained about cloudy water, foul smelling, taste of chemicals, there was E. coli outbreaks, and the city's water treatment plant wasn't capable of adding corrosion control treatment, and the city didn't have the money to upgrade the equipment. Eventually, the city switched back to using Lake Huron water. Now, does the city of Flint have a hospital? You bet. Does the water crisis impact the hospital? Yeah. According to hospital officials, yes. And most of the deaths that happened in Flint due to the water were connected to the hospital, and the hospital put that blame on the city's decision to switch the water supply. Now, the CDC says the hospital had issues that predated the water switch, and the reality is both. The hospital did have systemic issues for years, manageable perhaps, and the switch in the water supply exacerbated that situation, making it unsustainable. Here's the thing, when it gets to courtrooms, federal judges and civil lawsuits and pulling money with the state and city and the local engineering firm that you hired to pay for civil claims, you're losing and you've lost. You've lost your reputation and your good standing in the community. And it's a tough uphill battle to win back that confidence. So your hospital doesn't need to be Flint, Michigan to feel the effects of how municipal water supply can impact the work that you do in the hospital. For the SPS, the quality of water and the changes of the water, quality of water, can have a dramatic impact on what's happening in the 4 walls of your work area. First, the quality of incoming water can impact performance of the water treatment equipment inside the hospital. If there's hardness in the water, and that increases dramatically, your water softeners now are working harder. They use more salt, and they need more frequent regenerations. We've seen facilities where they've seen a significant drop in the department water pressure during the facility's regeneration of their water softener equipment. Or worse, the system bypasses softeners during regeneration, and the SPS is fed very hard water during that regeneration cycle. Now, the production of purified water for final rinsing is also impacted by the incoming water to the facility. The more dissolved solids in the water, the more your reverse osmosis and deionization treatment system must work. DI tank treatments, for instance, may become more frequent. RO membranes may become fouled more quickly and need to be replaced. And if you're not watching and monitoring this equipment closely, and what I mean by that is you're only just checking in once a month to see how things are doing, you may miss the incoming water. It's changed dramatically since your last checkpoint. And it's impacting the planned PN schedule on your water treatment equipment. When water enters your facility, it can change again. Your facility may treat water coming in for a number of reasons, and it may be treating the water, for instance, to feed the boilers that produces your steam. Any process that the water goes through, the piping it travels through, and where it goes before it comes to your department can be a potential source of problems. Hospital plumbing can be old. The corrosion to the pipes that happen in Flint, Michigan can also happen on your campus and inside your building. Now, we work with hospitals where the municipality provides glowing water reports because its samples are taken at the source, not if it's traveled miles of pipes. And large cities have water sampling stations. But again, if the piping from that location to your department is aged and corroded, that pristine water that's described in this beautifully formatted annual report from the Municipal Water Board is a lot less pristine when it gets to you, right? And it gets to the sinks, the washers, and the sterilizers in your department. And different water chemistry can change the effectiveness of enzymatic agents. So more detergents may be needed to properly clean the instruments. And if you're not catching that, you're not cleaning your instruments well. Now, you can also go the other way. If you're using excessive detergents, they may leave residuals on the surfaces of instruments, and that can cause staining. The steam in your sterilizers are also impacted by the quality of the water feeding them. And while the facility maintenance departments can be very sophisticated in the methods they use to treat the steam feed water and install things like steam filters to remove contaminants and excessive moisture, that balance can be very delicate. And like the city in Flint, there may be limitations on just how much water quality can vary before it starts to impact the performance of the steam sterilizers, and issues like wet packs become more common. All right, so let's talk about some characteristics that can affect the departments. There are many chemical and physical aspects of the water that flow through the SPS that affect your success. So if you look on this slide right here, there's a whole bunch of things that an alphabet soup. The AME TIR 34 guide, Water for the Reprocessing of Medical Devices, identifies 11 different water quality parameters to monitor and test. Now, there's an upcoming standard from AME called ST108. Should be coming out probably sometime later this year. Identifies 18 different parameters to monitor and test on the utility water, on the critical water, and the steam used on the SPS. And I could spend much of my remaining time going through each and every one of these parameters and how they affect what you're doing in the performance of the reprocessing equipment and the cleaning and the disinfecting and the sterilization of instruments and what levels are acceptable. So does this mean we all need to go back to school and become chemists? No, but a basic understanding will help you run a successful SPS. And I encourage all of you to read the AME guideline and the new standard when it's released. Each document is less than 80 pages. It's worth your investment. Let me just go over one parameter to give you an example of what the impact these things can have. Talk about chlorides. So for utility water use, AME TR 34 recommends that the chloride content in utility water be less than 250 milligrams per liter. When it comes to final rinse, it should be less than 1. Now, don't assume that your RO treated water is going to sufficiently produce water to AME guidelines. Right? If your water, let's say utility water, has a chloride level of 200, your RO is going to reduce 95 to 99% of the contaminants. That sounds amazing. But that also means you're going to have a chloride level that's going to be somewhere between 2 and 10 milligrams per liter. That's great, right? It's impressive, but it's still too high to meet the requirements for the AME critical water. right? So your final rinse, no good. So you're gonna have to probably add like a post-DI treatment after the RO in order to have high quality water, right? So if your utility water chloride is, let's say, less than 20, your RO will do a fantastic job reducing that chloride level to less than 1. But let's just say your pH starts to go up. You go over 0.8, 0.5, and or there's chlorine in the water. Now your RO membranes, right, are going to be compromised. They're going to be degraded. And the RO product water that's produced is not going to be less than 1. And if you're only checking your pH and your chlorine monthly or annually, you might be producing elevated chloride levels in your final rinse and not even know about it until you do your next monthly chloride test, right? Or your next quarterly one, or the next annual one. And it might be slight corrosion damage on your instruments. That'll be the first clue that you have that something's not right. I worked with one hospital where the DI tanks were not being exchanged on a regular schedule. And after several months, they were seeing corrosion on their surgical instruments and ordering new ones without any understanding of why it was happening. All right, so I want to talk a little bit about some of the sources of water problems, and I've put up a little fishbone diagram in here. So there are a lot of things that are difficult to control in the SPS to ensure consistent excellence in processing instruments. And variables like insufficient manually cleaning, improper loading of reprocessing equipment, incorrect wrapping of sterilization cases, operator errors on third shift on the equipment, can make you feel like you're playing whack-a-mole, right? Trying to eliminate the issues and reduce defects and rework on the instruments and trying to turn that around for the surgical team. And as soon as you solve one this pops up here, solve that one, this one pops back up again. So even within the narrow focus of just looking at water-related issues, everything from the treatment equipment to the water testing protocol can be the root cause of issues in the department. And a fishbone diagram on this slide shows the potential root causes for issues in the SPS due to water-related items such as materials, equipment, people, processes, maintenance, even the environment. You know, the classic categories used for troubleshooting analysis. Only this is tailored for water issues in the SPS department. So how many of these potential factors do you look into the last time you had a challenge in your SPS? So here's the point. Water and water problems, it's not always straightforward, not always simple. And many items can compound to create an issue. And like in Flint, an existing problem that might be manageable one day may result in reprocessing equipment faults and shutdowns when the system's overtaxed. Attentive, expensive repairs and extensive downtime can result. And I've talked with hospitals that end up investing hundreds of thousands of dollars in new reprocessing equipment because their current equipment was compromised by poor water quality, so that equipment's performance was no longer reliable or maintainable. And here's the crazy part of it. If you're just replacing that expensive equipment and you're not doing anything to treat that water or monitor that water, ensure that it's not going to have the same thing happen again, the whole process is going to repeat. And I've seen hospitals go through extensive fishbone diagram analysis trying to determine the root cause or the causes of issues they're experiencing. The number of factors, it's not infinite, but it's also not insignificant. I've watched an SPS manager spend 6 months investigating everything from the training of their ever-changing staff to outside weather patterns to see if the outdoor weather patterns were changing the humidity in the workspace and coinciding with the increase in the wet packs that they were experiencing. And a comprehensive water analysis told me in 1 week that's something they hadn't been able to determine over months. And that was that after all the other factors may contribute to the issue, it was poor quality steam feed water and an undersized SPS dedicated boiler that were the main culprits. And I've seen hospitals jump through hoops because of the laboratories that collected the samples and tested made mistakes, used the wrong testing procedures that concealed a problem, or made them think that they had a problem that they didn't. I've had laboratories ask if I could throw out bad bacteria results, like, hey, we'll take out the high one, we'll take out the low one. Like we're in the Olympics and we're grading gymnastics or ice skaters, right? Or they could take an average of all the readings, right? As if the high bacteria reading at a particular sampling port is somehow nullified by statistically lowering it by weighting in other sampling points, right? Crazy. Our philosophy at MMIC is to tackle the issues of your water and make sure it's the one branch of your fishbone diagram that's not a contributing factor to the problem you're experiencing, right? So simplify the issue, right? Make yourself bulletproof in that area. And then if you know that part's good, you can then focus your areas on other aspects going to be changing it. For example, in our lease fleet of mobile SPS, we raise the temperature of the purified water above pasteurization temperature. So bacteria contamination at point of use, it's just a non-issue, right? So if I got a customer and they using our lease fleet, the lab gives them a test from our water and say, hey, it's elevated bacteria. I said, can't be, the water's too hot. And now we're looking at okay, what's really causing this bacteria? Is it something to do with the handling? Is it something to do with the testing? So think to yourself, is there something that I can do in my facility and in my department that can make us bulletproof against some of these issues that I've mentioned or some of them that you see on the screen? How can you better monitor or manage your water? Because the fact is, it's a dynamic process and it's a job that never ends. All right, so I want to talk about a few case studies to illustrate some of these issues and how they impacted actual hospitals, attempts they may have taken, and ultimately what fixed the water problem. So the first case is about a rural hospital that had no major issue for decades with the reprocessing of medical devices and instruments. Right? Then something happened. The town experienced a water main break that took the better part of a week to completely fix. And the buildup and the inside of those pipes feeding the hospital that had accumulated over decades had started to dry out. And when water pressures were restored, the hospital started experiencing discoloration, staining, and spotting because all that gunk started coming down through and into the hospital. So they were examining their processes. Maybe it was something they were doing incorrectly. And they couldn't correlate the staining to what they were doing or what they were not doing. And changes in temperature and fluctuation from the warmer weather to cold weather and then back again in the late fall, well, that resulted in municipal water line breaks. So the municipality, they went in there, they fixed the leaks, turned the water back on, and another leak was discovered and they had to fix that. None of that was helping the hospital in maintaining high quality water. In one particular week, 99% of all the sterilization cases processed were rejected by the OR team. So surgeries were getting postponed, getting canceled. Patients and families were unhappy. They took out their frustrations on their doctors who had little control of the quality of the cleaning of the medical instruments. I'm guessing prior to this that most of the doctors hearing patient frustrations couldn't find their way to the SPS department if asked. The doctors were getting frustrated and threatened to leave if the hospital had any more cancellations. Eventually, a high-risk patient had bypass surgery canceled while they were waiting on the operating table. And the surgical team noticed spotting instruments. So that patient reached out to the U.S. Senator, and well, let's just say you would not want to have been in that hospital to have to deal with that fallout. So the hospital started their analysis with the water and worked their way one step at a time to the sterilized instruments. And eventually the hospital pinpointed the source of the issue, steam feed water. The facility was using plant or facility steam. And while the quality of steam was adequate for non-critical uses, it just wasn't for sterile reprocessing. And while the quality of the steam had been adequate previously, it was marginal. And that repair work on those water lines was just enough to cause major havoc inside the hospital. So the problem fix was easy to state, but difficult to implement. Provide better quality steam feed water to the boilers. Great. But the boilers and the steam piping was designed for municipal grade water, not highly processed water. Like the city of Flint, their equipment was not designed to handle a water quality issue that they were experiencing. So the facility developed a short-term and a long-term solution. In the short term, they leased a temporary mobile facility that purified the municipal water, removed the impurities causing the staining and spotting. Sterilizers with integrated steam generators were installed, eliminating the need to treat steam produced for the entire facility, right? So we're just doing steam for the department. And because these steam generators weren't designed to handle purified water, a food-grade polyphosphate was added to the steam feed water to raise the conductivity of the feed water to a level where the steam generators could function properly. And as soon as the temporary setup was operational, staining issue went away. The long-term solution was to duplicate the successful short-term solution mobile setup inside the facility. So, key takeaways. One, understand that issues with processing instruments can originate with causes that are outside of the facility. Have a plan for when bad things happen is a good idea. A fishbone analysis approach to determine the root cause was excellent, but that took time, and the facility ended up having bad publicity over that situation. So what's your plan B if you start having issues in your current SPS and you can't keep up with the surgical demand for your instruments, right? Trying to produce a plan in the middle of a crisis can lead to stressed and sometimes bad decisions. Two, maintain good communication with the local water authority. Understand their work can impact your water quality in SPS. The hospital did initially connect the dots between the work taking place outside the hospital and the defects they were seeing on the processed medical instruments. Know that the work taking place on the water lines feeds the hospitals, impact the hospital, impacts you. And local municipalities can and will change their water treatments. They sometimes shock the system with disinfectants. They sometimes flush out the systems, resulting in downstream silt and contaminants entering the hospital piping. Three, your system may be operational, it may be adequate, and it may be successful, but is it capable when it's stressed? So how close are you to that edge that you're operating your water system? Is the hospital's water treatment equipment designed to handle the unexpected? And if not, what happens when the unexpected happens? The hospital steam feed water did not meet AAMI TR 34 recommendations. And I'm guessing that the people in the SPS and the facility maintenance department didn't realize that. I mean, it was never a problem before for decades. And there was no incentive to change what they were doing until it became a problem, right? The old adage, it's not a problem until it is a problem, and then it's a big problem. All right, I want to talk about the second case study, right? This is about a hospital that installed brand new sterilizers. Now, they knew that high quality steam feeder was key to successful steam sterilization. So they purchased sterilization models with integrated steam sterilizers designed to run off purified water. So you would have thought that they were talking to the hospitals in case study one, right? And it was awesome. They everything ran great. It ran through the fall and the winter and the spring. In fact, everything ran fine for the first full year. However, the second year they were operating with these new sterilizers, they started seeing their sterilizers having faults, or having vacuum faults to be precise. So like the horror story of case study one, the faults became more frequent, resulting in rework and re-sterilization of instruments that had been interrupted in the sterilization cycle. That rework started impacting the surgical team's ability to perform the surgeries. And I'm sounding like a broken record, right? Then they started having to cancel surgeries. So what's going on here? I mean, aren't they doing everything correctly when it comes to water quality? So the issue is small, but it's a significant one. These new sterilizers were designed with vacuum pumps that required facility water to act as a cooling medium. So during the winter months, when the water temperature was perfect, now that second summer at the facility was a hot one. There were multiple heat waves, and the water supply came from the local river. And as the summer wore on, the municipal water temperature rose. Now the sterilizer's vacuum pumps were designed to be cooled with water no hotter than 68 degrees Fahrenheit. And they continued to perform as the water temperature rose and went above 70, and then above 75. But when the river's water temperature got to 85 degrees, the vacuum pumps started to fail. Now, replacing the failed vacuum pumps helped temporarily fix the problem, right? That's the short-term fix. But operating the vacuum pumps without adequately liquid cooling was reducing, one, the vacuum capacity of the pumps themselves, and two, stressing the pumps, so they were likely to have to be replaced again soon in the near future. So the long-term solution was to provide a chilled water to the sterilizers meant to cool the vacuum pumps and separate this water from other utility water used in the SPS. This chilled water was recirculated locally to minimize the gallon per minute consumption of the chilled water in the department. All right, key takeaways, right? Water temperature, and I might add, water pressure, are also aspects of water quality, right? Don't get so hung up about looking at those tables in AMI TR34 and looking at the big 6 or the big 8, wherever it is. These water temperature and pressure are just as important, can cause just as many problems. When the equipment was installed, no one looked at the possibility of the water temperature seasonally fluctuating and that impacting equipment performance. Quick question, how much of the water temperature at your hospital changed over the course of the year? Are you even checking this? The facility and the SPS were laser focused on that AMI TR34 for washing and for rinsing and for sterilization of instruments. They didn't look closely at the non-AMI compliant water requirements that the OEM, equipment manufacturer had for it, because that water wasn't touching the instruments. And here's a fun fact. Utilities are often the common root cause for medical equipment issues. So water chemistry, water pressure, water temperature, they are all important. Don't forget about your drains. So if you have underside drains that back up, that can cause sterilizers and washers to fault. And we're talking about water today, right? But just how clean is your power, right? And if your sterilizers use compressed air, how consistent is your pressure and your dew point of the compressed air, right? All these factors need to be considered. All right, I want to talk about another case. It's a fun case study because we're going to talk about a facility that had no problems. So as part of a monthly water testing to validate the SPS water quality, water hardness and conductivity was tested on the critical water. That is the water used for the final rinse at the 3 base sinks and the washer disinfectors. Now the AMI TIR34 guideline recommends that the final rinse water conductivity be very low, right? Below 10 microsiemens per centimeter. And very low water hardness, less than 1 milligram per liter. Now, for those of you who are familiar with water conductivity, conductivity is closely related to total dissolved solids, or TDS. And the conversion factor, which ranges from about 0.5 to 0.8, is often used, depending on the conductivity of the water, or the specific ions in the water, blah, 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 right? So conversion factor is sometimes used about 0.67, but it's somewhere between 0.5 and 0.8 for your water. Well, why am I saying this? What does this mean? Well, with a conductivity reading of 10 microsiemens per centimeter, that would convert to approximately 6.7 milligrams per liter of TDS. Though to be safe, you could estimate you're probably somewhere between 5 to 8. Notice that TDS milligram per liter numerical value, 5 to 8, is less than the conductivity numerical value, 10. So at this particular hospital, the local laboratory performed the conductivity and the hardness test and reported that the critical final rinse water conductivity was 2 microsiemens per cm, and the water hardness was 30 milligrams per liter. So the first number was great, right? 2 microsiemens per centimeter. It's under the 10 microsiemen threshold. Perfect. Hardness, however, was a red flag, right? 30 milligrams per liter? It's supposed to be less than 1. We're way over the maximum hardness for final rinse water. So the protocol was to retest, and this was done. Results came back, again, exceeded the limit. So the protocol would be to stop using the critical water until the water hardness issue was resolved. But the hardening readings didn't make any sense to me. If your water has a conductivity of 2, that's approximately 1.3 milligrams per liter of TDS, total dissolved solids. You want to use that 0.5 to 0.8 conversion factor. I would expect that TDS to be no lower than, let's say 1, but no higher than 1.6 milligrams per liter. So the total dissolved solids in the water, which includes the dissolved calcium and magnesium salts that are responsible for the hardness of your water, was no greater than 1.6. So if that's the case, how could the laboratory measure water hardness that exceeded 1.6? How could they be measuring it at 30? So I called up on the hospital's behalf, spoke to the laboratory manager. They said they would pull up the analysis, they would review, they would call me back. Did, and he called me back to inform me that they had checked over the processes, they checked over the procedures and the calculations used with that test method, and everything checked okay. So what does that mean, I asked? Well, it means we did everything correctly and the hardness readings is accurate. So how? Now I explained to them that either the hardness reading was incorrect or the conductivity reading was incorrect. And they said, no. Conduct reading test, that we did that correct as well. So I said, well, how do you explain this obvious contradiction? Like, yeah, I see your point. But I stand behind our laboratory's results, and I'm happy to state in front of the hospital committee, tell them this fact, right? So that's not very helpful. So the solution to the problem was to test the water with a different laboratory, which we did. And it, of course, indicated a much lower hardness. It was actually 0.5, right? I had a similar, but a different experience at another site where the local water test laboratory was showing a steady increase of water hardness in the utility water over the past several months, from a historical average of over about 110 milligrams per liter. And it ranged from about 68 on the low side up to about 188, the worst of months, right? So over time, though, in recent months, that was increasing. That was going up. So the hardness readings were over 200, and then it actually spiked up to 350 milligrams per liter, right? So first of all, you're just way over the AMI threshold of what's acceptable water to be using in your SBS. So this potentially is a major issue. Wow, we got to treat all the water, all the utility water. But one red flag made me question this new trend for our customer. When the water hardness got to 350, the hardness after the softener feeding the RO system was reading 180. So the customer either had an out-of-control water hardness issue and a malfunctioning water softener, or these results just weren't correct. So a call to this laboratory manager returned a response. Calculations were checked. The readings were accurate. Right? Here's the story again, the same thing, right? So we resolved this issue by testing the water ourselves with hardness test strips. And we're getting closer to 100 milligrams per liter, which matched closely to the historical average. So a follow-up with the laboratory revealed that a new technician had taken over testing of water hardness and running analysis. And while the calculations were correct, the test method had not been followed and the titration technique was incorrect. So the results are bogus for both labs. I worked with one laboratory that was drawing samples for bacteria testing, and it was common for the samples to indicate over the allowable threshold, right? Retests were frequent. SPS were having shutdowns for critical water disinfectings, and that's common. Shutdowns, the whole story, cancellations, surgery impacts, etc. So I started looking at these reports that they're creating for my customer closely. One, they're waiting more than 24 hours to begin the incubation of the samples. Well, the requirement is it should be done the same day, or if you chill it, it has to begin within 24 hours. So they were chilling the samples, right? But they're keeping it past 24 hours. The other thing I noticed was they were holding them overnight chilled, but not cold enough. They're keeping me at 50 degrees. They're supposed to be keeping it at 36 degrees. No warmer than 39 degrees. So when I discussed it with the laboratory manager, he insisted they were doing everything by the book. So I opened up the book. I opened up the TIR 34 guideline. I opened up the APHA standard, methods for testing water for bacteria, and I went over and reviewed it with them. And while I could not make them agree that what was written down in the standard was different than what the protocol that they were following, the end solution was twofold. Going forward, we started using different laboratories following APHA and AMI standards and guidelines. And two, we offered the customer that we would test their water for bacteria at our own headquarters. We have a small testing laboratory set up where we follow the protocols as defined by APHA and AMI. So takeaways on that. One, everyone and every laboratory is fallible. Two, do not blindly trust water results. Study the results. Do they make sense? Do they map to historical averages and ranges that you would expect? Is the laboratory following the protocols, the procedures, and the methods correctly? And if you don't feel qualified to audit it and check their work yourself, then have someone else do it, or send out samples to a second lab and compare the results. And four, is the laboratory document what they're doing? Are they documenting the chain of command for samples taken? Are they recording when samples are taken, their temperatures, and the date, time, and temperatures when the analysis is started? And readings like things like pH have a very short hold time, 15 minutes. So if the laboratory is drawing a sample and they're checking pH 15 days later, well, that's not a valid result. Last thing, have a historical data is a huge benefit to troubleshooting and getting to the root cause of issues. Right? So not only could I look back on the historical data for averages, for ranges, and for trends in the water test, we also had data on the performance of the water softener. So we knew that that probably wasn't the issue. All right, last case study here. I want to talk about a hospital spent a lot of time and money building a new SPS department, but neglected the finer points of the work being done and resulted in lengthy delays, months that is, in their go live date. Now, by all accounts, the water purification was perfect. They were producing excellent and high quality purified water for their critical water use inside the new SPS department. Check. An initial water test for bacteria for HPC showed an HPC reading of 11 CFUs per milliliter. Requirement is be less than 10. So yeah, you're on that threshold. The next time they checked it was a few weeks later, it was now 20. So they start checking more sampling locations the next time, and they saw point of use samples ranging anywhere from less than 1 to over 1,400 CFUs. 9 months later, they were still getting HPC readings ranging from 2 to 60 CFUs. So MMIC came in, asked to examine and look at the setup and give some suggestions and consultative engagement. So we looked at the water treatment equipment, we looked at their sampling ports, we looked at the routing of the critical water piping through the department, the connections to the critical water to the equipment inside the SPS. We also asked how the critical water system was being maintained while they were in limbo. And our site visit revealed several observations and recommendations. One, several of the sampling ports were not installed in the line of flow, but off a T, producing a small dead leg of stagnant water by the sampling port. Let me just kind of flip it into that. All right, so you can see this on the second image to the right, right? So the water's flowing. This sampling port on this right-hand side, water is not flowing past it. Water is stagnant there, right? This one over here, this sampling port, again, it's better, but still a little bit of a dead leg of stagnant water in here, what I find more offensive is they put the sampling port right next to the light switch down here. So anytime someone goes into the room to turn the light switch on, there's a good chance they're going to flip their finger and touch the sampling port itself. Now, any bacteria, anything they have on their fingers is on the sampling port. Someone goes to test the water, they're not just testing the bacteria in the water, they're also testing the bacteria on someone's finger. So anyways, the other thing too about these sampling ports, not zero dead leg valves, so they allow a fair amount of water to sit around in crevices around the sampling port spigot. In essence, biofilms were being allowed to form where they were testing the water. And with water being drawn only once a month, this led to slow progression of biofilm growth, and with each ensuing month. And the drops from the critical water recirculation loop to the equipment was also significant. So while the AAMI TI-34 recommended no more than 6 times the pipe diameter for dead legs and branches that did not run continuously, right, connections to equipment like the ultrasonic dropped from a recirculation loop that was in the ceiling 10 feet up down to the floor, which then connected to a 6-foot stainless steel braided hose, which then connected to the ultrasonic. So 16 feet of dead leg when that pipe diameter said you should have had no more than 6 inches. Lastly, the system was not being regularly disinfected. The AAMI protocol is for, at a minimum, monthly disinfections. And the rationale, I believe, in the hospital was, well, this new SPS has not gone live, so it isn't necessary to regularly disinfect the system. So, key takeaways. 1, the devil's in the details. The best intention of the management of the general contractor is lost if the plumber doing the work doesn't understand the importance of maintaining minimal lengths on dead legs. Remember, connections to equipment that doesn't run continuously can be a potential dead leg issue. After 4 hours of non-use, a branch of piping to a piece of equipment that doesn't run, that stagnant water can start forming biofilms. So does your SPS run continuously overnight, over the weekend, over holidays? If not, what's your plan to make sure you don't have biofilms forming in the inside walls of your piping? Now, I've seen plumbers plumb secondary loops, branching off a main loop. These secondary loops were a smaller pipe diameter, feeding sinks and washers and ultrasonics. And the best intentions had now been ruined or compromised by poor execution because the plumber doesn't understand the significance of the work that they're doing. So who's checking the work of the plumbers? Are you reviewing the SOWs with the actual plumbers doing the work so they understand exactly what you want to accomplish? As soon as you start producing purified water, right, you need to have the mindset that this is operational. Even if you're not operational, that water system is. The clock now is ticking on your maintenance and your upkeep. You should be doing regular disinfectants should be occurring. There should be water testing and equipment maintenance. At my company, what we do is we get system up and running, we test for bacteria. Great, we get the results back, we test the second week. Boom, we prove we got 2 weeks in a row, no bacteria. We test a third week. We've now proved we got 3 weeks in a row, no bacteria. We test a fourth week. Right? Got 4 weeks of data, now I disinfect. Right? So now what have I done? I proved that I can go 30 days without bacteria growth, and then I'm disinfecting on a regular basis, on a monthly basis. I now have data to prove that once a month is adequate for my department, for my system. Right? At this site, we saw an ultrasonic that was plugged into a wall outlet, and since that outlet was ground fault protected, it got splashed by water and it tripped, turned off the UV light. For how long, no one knew. So a key element for controlling bacteria growth in the system was off and unchecked for potentially months. Okay? So again, you have to maintain the systems even if you're not, quote unquote, using it. Lastly, sample ports on critical water should be designed to minimize stagnant water around the port and areas where bacteria can grow. Don't leave it up to the plumber to pick out a port, sample port, a spigot, or something that they think this will work. Right? Anyways, so I just want to quickly summarize. There's a lot of water quality parameters that determine quality. There's a lot of things that can affect water, right? managing water quality takes out a well thought out plan. Remember I mentioned early on, have a quality assurance plan, right? Know what it is you want to monitor. Know what it is that you want to check. What's the frequency of checking, right? What are you going to do when something goes out? What's going to be your plan, right? And the other thing, managing water quality is a continuous process, right? Don't fall asleep at the wheel. That first case study, decades had gone by. Decades, not a problem. Like the Maytag repairman fell asleep at the wheel because nothing was going wrong, right? But it's a continuous, ongoing process. You're always going to be trying to check it, monitor, confirm everything's going great. And the other thing is managing water, it's a multifunctional activity. No one person is going to be on top of this stuff. I mentioned plumbers, I mentioned laboratory stuff, I mentioned all kinds of stuff in there. No one person is going to have all the answers to this stuff. So you have to think about what's the team and who's on my team is going to help make sure that we're on top of all this. Anyways, that's it in summary. So I pass it back to you, Lindsay.
All right, Len, thank you so much. It's very easy to see the passion that you have about this information when you start getting into the case studies and the real world, real life examples of water quality issues. And honestly, how you've been able to help these facilities solve them, which I think is so, so powerful. We do have a couple of minutes for questions, and I do have a couple questions waiting for you. If anyone has specific questions related to these case studies or related to water quality at your own facility, like I said, I'll keep them confidential, but definitely enter those in the Q&A tool on the lower left-hand side of your screen. Len, if you don't mind, I'm just gonna spitball some questions at you,
Okay.
and we can kind of use up these last 8 minutes that way. One question that came in is, I'm about to go through a remodel. How do I know if the plumber is doing the plumbing right, and who would know to double check if it's being correct?
Right. So the first thing, that plumber is working off some sort of statement of work. And if you've hired an engineering firm, if you've hired a general contractor, how do they come up with that statement of work? How do they write that? What do they do to write it down? So it's really easy to say, here's all the different pieces of equipment. You need to connect them all. And I need one line of cold water. I need one line of hot water. I need one line of critical water, right? But again, it's the devil's in the details. You've got to get down to the level of, are you putting out specifically, how is this going to connect there? I need this thing to come in a loop on my critical water, and it needs to come right to that piece of equipment. How far away is acceptable? When you do a statement of work, then that's almost your template for how you're going to check that work is being complete and sign off. It's your verification, right, that work is done complete. So if you don't put down no more than X amount of distance between the loop and that piece of equipment where the connection point is, you don't have a checkbox there anymore, right? So think of all the things you want your general contractor yourself to go through and check mark. So you can put down, hey, it's 6 times. What's the size of the pipe? It's 2 inches. Okay, 6 times 2. That comes from the AME TR 34. My suggestion would be, whoever is going to be doing that work, give them that standard, give them that guideline, have them read it over, or you regurgitate it to them and explain, these are the key things in this guideline that need to be followed. And if you're not familiar with it, and if you're not comfortable and saying, I'm not too sure what's important in this guideline, you're going to need to reach out to someone who is. And there's a lot of people out there who have been doing this for years who are expert. The thing I would caution against is, I've definitely come across people who say they are experts and they know it, and oh yeah, sure. And then you ask them questions about it and they've got it wrong. It's not accurate. Or they say, well, all that stuff, that's nice, but I've been doing this stuff for years and it's not a big deal, right? Those are some red flags. If anyone sort of dismisses of those AME guidelines, it's not really, don't worry about that. It's a big deal. That's one flag on it. But if you, I'm happy, if you want to reach out to me, I'm happy to kind of answer your questions on that stuff, but find a resource that you feel confident and comfortable in. Do they have experience doing these sort of things elsewhere? Can you go visit those sites? Talk to those departments. How did it go well for them? How long did it take them to get up? What are the issues in getting up and running? Do they do water testing? Do they do the things that you would want to do in your facility to make sure your water is being maintained? So be really rigorous about it. We go in there and we'll put in like a detail blow up saying here is coming into this piece of equipment, and if the piece of equipment has a connection point at the foot of it, right, and the water's got to come all the way from the ceiling, or in some cases we've had it where the connection point is at the top of the machine, but then the water goes all the way to the bottom. There's a slug of water that's 5-6 feet that's going to sit in there. So it's like the equipment manufacturer may not, there may be multiple positions where you could connect up to. So you really got to get into the details of it. Don't take it for granted, because like that one hospital, 9 months, because no one was really paying close attention. They just trusted that general contractor to run with it and take care of it. They had enough issues to deal with patients and surgeries. Someone else has got control of this, and I don't need to worry about it. And that's going to bite you.
Thank you for answering that question. This next question came in, says, where in TIR 34 can I find that the sample ports need to be at the equipment in SPS?
Where the sample ports need to be the equipment?
Need to be at the equipment in SPS.
Yeah, so that's a really good question. And I'm in the committee meetings for the AME work group for ST108. So in the first section, and I think I have it in here. If you look at the first section in TR 34, they'll go through like a list of like a glossary of common term uses. And I think they'll refer to it as point of use, right? Something along those lines. So that would be section 2, right? So that's an alphabetical. So point of use, right? And they'll talk about water treatment system in which purification, use of filtration takes place just before a single water supply outlet. So I think what Amy realized, there was a lot of ambiguity as to what that meant and where you needed to sample. So it's clear. It says very clear you need to sample your water wherever you're producing purified water. The water that's going into the department, you need to sample it there for bacteria. When it comes back from the department to the place where you're generating your purified water, you got this thing in a recirculation loop. You test it there. So you have an out sample, you have a return sample, and then it says point of use in the department. Now, every hospital may define it differently. So I've seen some hospitals say, for us, every single piece of equipment, we're going to put a sampling port on it. Right where it leaves that branch, boom, I'm going to sample it here. So that's great if you have 3 pieces of equipment in your department. But if you have let's say you've got 5 washers and 7 sterilizers and, a half a dozen sinks and a few ultrasonics, that's a lot of sampling ports. And when you put in a sampling port, you can't just say, well, you know what, I just won't sample this thing. I'll sample this once at the beginning, and then I won't sample again for another year. Because that sampling port can then start growing bacteria in it, right? So now you set yourself up, okay, and I'm drawing 15 samples for bacteria each and every, that's really expensive. So some hospitals say, hey, we're just going to group it up. One sampling port for all these washers are next to each other. We'll do one for all the washers. All the sinks are sort of, along this wall. We'll do one for here. We're using the water that's going for the sterilizer to produce steam. We'll have one that's for that area. For the car washers, we'll have another one there. That's still a lot, but it's a lot less. And ST108, and it's not finalized. We're voting on it. I think the votes are in the next week and a half. I think the verbiage we're going to see is going to say it's acceptable to say the very first place where your water meets the first piece of equipment they use as your critical water, right? So coming into the department, that one can be acceptable as your point of use, and you don't necessarily have to go and have 16 or 8 or something like that. But ultimately, here's the thing. They're putting a bar and as a bare minimum. What are you comfortable with? So I'll just point this thing. It's great to say, hey, the first piece of equipment it comes into is X. I don't know what that X is that's going to be. It depends on your plumbing system. Let's just say it's a washer. Let's just say it's a car washer. I don't know, right? I got my sample report there, right? If I have 5 3-bay sinks and each of them have a final rinse faucet on there, right? I would tell you, when you use that faucet, because you're not running that all the time, there's a really good chance that when you pour water out of there, you may be getting bacteria out of there. It's like the faucet in your home, right? You know, you say like, where you go to a hotel, hey, you should kind of let that run for a minute or two, right? So my suggestion on a personal level would be, look at your point of use where you have those manual sinks, because no machine is turning on the turn. That's just a person going on and turn those things on. And so you may be more comfortable saying, we're going to check at every faucet, every manual faucet, and make sure we're not growing bacteria in there, and maybe another place or two, and that makes us comfortable. What is going to make you comfortable? Because ultimately, your washing instruments, they're going to be going in performing surgery. I mean, if that was you getting the surgery, if that was your parent or your child, your spouse having surgery, would you be comfortable? Right? So I say use that, because that's what we do. What would make me comfortable if it was me being operated on by these, what kind of testing would I want to do to make myself, not like what's the cheapest way, what's the minimum I have to do, what's going to be the one that's going to make me most comfortable, that we have a really rock solid setup.
I love that. I think you portrayed perfectly that balance between that minimum requirement required by standards and guidelines, and then also balancing that with your gut instinct and what makes you feel good, what makes you feel safe while meeting those guidelines and standards. So thank you for calling that out. I think that's a powerful statement. Len, I wish we had about 15 more minutes to address some of these great questions that have come through. Everyone who's submitted a question, I will make sure to get these to Len, and he'll reply back via email. And so we'll take a quick 10-minute break. Actually, it's more of an 8-minute break between this session and the next, but I want to make sure everyone has a chance to use the restroom, grab a snack, whatever you need to do before joining us for the following session. Len, thank you for sharing your passion with us in these case studies. I know it's a lot of great information that folks can take back and really put into good play in their departments.
Thank you for inviting. I really appreciate it. It's a lot of fun. It's a really great thing you guys are doing.
Awesome. And we'll talk to you later in one of the panel discussions.
Definitely. All right. See you later.
Thanks, everybody. Leave your browser window open. We'll transition you to the next session automatically. We'll see you in the next session.